Okay, good morning, everyone. Sure. So today, can you see my slides? Okay, please help me to make recordings. Okay, we have the lecture now. Okay, so for today we continue to study lecture 1, part 4. And then if we have more free time today, we continue to discuss about lecture 2. Okay, so again, from totally we have 16 classes for this course. So now this is 8 class. Okay, yeah. So that means we already finish half of the total class for this course. And please remember to submit your homework on time. Okay, so last week we discussed about elementary matrices. Okay, yeah, and we know how to determine the E, also the inverse of E. What does this mean? E is elementary matrix. Okay, so if we know E, we can get the inverse of E according to this table. Okay, so of course to get E or inverse of E, we should get I. Okay, identity matrix. Then you can get E and inverse of E. Okay, so any matrix A, we can apply Gaussian elimination. You can get A1, A2, blah blah blah, AK. Okay, and AK is identity matrix. Okay, so to get A1, we have E1 because we have I identity matrix. Okay, we apply the same elementary operation. You can get E1 and you can get E2. Yeah, blah blah blah. You can get EK. Okay, of course, you should remember for AK, so AK is identity matrix. Okay, after that we can get inverse of A, right? Inverse of A is EK times EK is minus 1, blah blah blah, times E2 times E1. Okay, so this is the second way to determine the inverse of A. Okay, yeah. So that is the reason why we figure out elementary matrices. Okay, because when we take the products of all the elementary matrices, you can get the inverse of A. Okay, and last week I also discussed about the advantages of this method, right? Because we try to reduce the size of the matrix. For example, if we apply traditional method, okay, for example, we have A, N, and N. So here we have N rows, right? And 2N columns. Okay, so we increase the size of the matrix. So maybe it will take us a long time to get inverse of A. Okay, so that's the reason we think about another methods. We apply elementary matrices. Okay, yeah. This is N, right? And then now we consider some examples of determination of inverse of A. Okay. So here we have matrix A. Matrix A we have 3 rows and 3 columns. So that means we need I3. Okay. Yeah. For our modification. Okay. 1 0 0 0 1 0 0 0 1. Okay. Yeah. So we try to modify A to becomes identity matrix, right? Okay. That means equal to AK. So here, the first step. The first step, okay. So look, this is A, right? 1 2 3 2 5 3 1 0 8. This is matrix A. Okay. So if we add this minus 2 times the first row, okay, this is R1, R2, R3. Okay, so if we time minus 2 with R1 and then plus R2 related to R2, you can get A1. Okay, here minus 2, right? Minus 4, minus 6, because we time minus 2 with R1. So you get here is 0, here is 1, here is minus 3. Okay, yeah. And then we also do the same there. Yeah, the same elementary operations with I. Okay, so I we have 2 minus 2 R1 plus R2 related to R2. So you get here is what? Here is 1 0 0, right? And then this arrow should be here. Okay, yeah. And then this is minus 2 0 0. So here you get minus 2, right? 0 plus 1, you get 1. This is 0 and blah blah. So this one is E1. Okay, and yeah, okay, we also applied the second, right? We add minus 1 with R1 and then plus R3 related to R3. Okay, yeah. So we can get what? Minus 1. Okay, minus 1 0 0. So here you get minus 1 0 and 1. Here you get minus 1, minus 2, minus 3. So you can get, anyway, you can get here is 0, minus 2, minus 3 plus 5, you get 5. Okay, so here I1 comes to A2. Yeah, so here you can get E2, E3, okay, E4, E5, E6, so E5. Okay, yeah, so after E5, okay, we get AK, right? And this is A5, this is A3, this is A4, this is A5. So A5 is identity matrix, okay? And then you can get A1, E2, E3, E4, E5. So if we take the A inverse, if we calculate inverse of A, this is E5 times E4 times E2 times E1 times E1, okay? E2, E3, E5, E4, E3, E2 times E1, okay? So you get inverse of A. Yeah. Inverse of A. Okay. This is the traditional method, right? This is traditional methods because this is AI we modify to get I inverse of A. Okay. Yeah, but if we apply E1, E2, you need to separate here. Okay. Anyway, we can make the comparison between the traditional methods and the new methods, not new, just these the second method. Okay, yeah. So here we need to separate this one because every elementary matrix we just apply the single elementary row or column operation. Okay, yeah, should remember that. Maybe we choose another example for more simplicity. Okay. Anyway, we have some exercise, so good to have you practice. Okay. So this is the special case because after some steps we have the zero rows, right? We have a zero row, so A is not invertible. Okay, we know before, right? So for summary, okay. So if we determine the sequence of elementary row operation, okay, you can guess inverse of A. So inverse A is EB or EK, right? Times blah 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 times is 1. Okay, yeah. And this one for the application of inverse of A. Okay, we discussed before. If we have AX is B, and from A we can get inverse of A. So we time inverse of A with A and X equal to inverse of A times B. So inverse of A times A, you get I times X is inverse of A. Okay, times B. So you can get the solution XE, you know, XE inverse of A, right? Times B. Okay, times B. Okay, yeah. So if we have x times A, you get the AX. Okay, and if we times inverse of A with A and X back to X. Okay, yeah, or we can understand this slide. Okay, like this. Okay, X is inverse of A times B. Okay. Okay, so this one for your reference. We also studied this one. Okay, column row expansion. Okay, now we go to the next one's LU factorization. Here is a definition of LU factorization. If we have we have n rows and n column like this. Okay, if n rows and n column matrix A can be written as the product of lower triangular matrix and upper triangular matrix. So lower like this. Okay, this is the format of lower triangular matrix, and this is the format of upper triangular matrix. Okay, so we can get A is L times U. Okay. Yeah. So A is L times U means LU factorization of A. Okay. So this one we say is a triangular matrix, right? Okay. Lower because the elements below the diagonal element. Okay. Should be non-zero values or zero values. That's okay. This is random. But if we consider the element above the diagonal element must be all zeros. Okay, we don't care about the values of A21, A31, but this is zero or non-zero value. But the element above the diagonal must be zero. Okay, here. Yeah, we say lower triangular matrix. So here, this is the diagonal element, right? Elements, right? So for the element the elements below diagonal must be 0. Okay, here must be 0. So this one we say is upper triangular matrix. Okay, yeah. As of course, the lower triangular matrix or upper triangular matrix, okay, they are on the square matrices. Okay. Any questions so far? Okay, we have some noise here. So today, please help me to keep heard, to be silent, okay, because it makes noise. Any questions? Yeah, question please. So if you have any question, just tell for TA and maybe TA will repeat to me, or you can type the message. Okay, so now we continue, and maybe we will come back to the questions. Okay, so now we try to make the relationship between LU factorization, A is LUs, and the sequence of elementary matrix we have EK is minus 1, blah, 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 time is 1. Okay, yeah. So we have some example first, okay. This is A, this is matrix A, and you can analyze A to becomes the LU factorization. Okay, this is L, this is U. Okay, why we know this is L lower triangular matrix? Because the element above the diagonal must be 0, and here this is for upper triangular matrix. Okay, yeah. Or here, you know, this is A. Yeah, this is A. Then this is L, and this one is U. Because A we have 3 rows and 3 columns, so L must be 3 rows and 3 columns, and U 3 and 3. Okay, and this is the diagonal element, right? So the elements above the diagonal must be 0. And for upper triangular matrix, the elements below the diagonal must be 0. Okay. Yeah. So now we think about this one. So if we have A, I modify A to become A1, to become A2, blah, 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 to get AK. Okay, right? And AK is like U, okay? Like use means upper. Okay, sorry, like, let me see. Yes, okay, this one is use, okay. What does this mean use? For example, here we have 3 rows and 3 columns. So after some step, you can get AK. K steps, you get AK. Then you get UK, okay. In UK, we have 3 rows and 3 columns, okay. So here, you can get the diagonal element, right? Okay, because this is upper, so all element here is 0, okay, and this is random, okay. So what is 6? What is 6? 46. Okay, so if you think about we apply the Gaussian elimination. Okay, so if we apply Gaussian elimination, right, you can get U, okay, after some steps. Okay, and from A1 you can get A1, right, because from A you get I3. Okay, and then we apply the same step to get A1, you can get A1, and here you can get A2, blah blah blah, you can get EK. Okay, so after K steps you can get U. Okay, you can get U. Or we can say UE EK times EK minus 1 blah 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 times E1 times A. So what is it? This is the theorem of elementary matrices, right? Okay. So from here, if I times inverse of EK, okay, inverse of EK minus 1, blah, 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 inverse of E1, okay, yeah, you can get here is A, right? And here A, inverse of E1, inverse of E2, blah, 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 inverse of EK times U. So what is it? This is L, okay, this is L. So now, if we apply the sequence of elementary matrices, okay, you can get U like this one. And if we know U, you can get L. So L is inverse of E1 times inverse of E2, blah, 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 times inverse of EK. So this is the application of the sequence of elementary matrices, okay, to have you determine L, okay. And when we apply Gaussian elimination, you can get U. So we take L and U, you can get A. Okay. Any questions? Maybe we come back to the questions. Okay. So the row operations we use on this slide 22 were just an application. Yes. Okay. Yes. So yes, correct. Okay. So as I mentioned before, this one for it's for AI to I inverse of A. Okay. So if we apply to the second method to get this one, you need to consider every step. We just apply the single elementary operator. So here you get A1, A2. Anyway, here you get A1, A2, many elementary matrix. Okay, you need to remember for yourself, and then you can get inverse of A. Okay, yeah. But of course, this is traditional methods. This is the first methods we apply this one. Okay, is it clear for you? Okay, good. Yeah, that's the reason I asked you to make the comparison for yourself. Okay, we apply the traditional methods. I mean this one to get inverse of A, and then we apply the second methods. We figure out the products of the sequence of elementary matrices. You can get inverse of A, and we compare the results together. Okay, so now for our LU factorization. Okay, this is very important. Yeah, so we have example. Okay, so again, okay, I will summarize for you. Okay, so now we have A is L times U. We would like to factorize A to become L times U. What is the format of L and what is the format of U? Okay, so A should be n row and n column because this is a square matrix, right? Okay, so you can get L. Okay, so L should be n rows and n columns. So here you have L11, okay, and blah 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 blah. and here you get L22, blah, 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 blah. And then here you get LNN. Do you agree with me? Okay, because we have n rows and n columns. So you get the diagonal should be like this. Okay, yeah. So for elementary, for element, for diagonal here, this is diagonal, right? Yeah. And for lower triangular matrix, okay, the elements above diagonal should be 0. So here is 0. Okay, 0. And then we have UNN is U11, blah, 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 UII, blah, blah, blah. Yes, UII. So this is diagonal element. This is diagonal elements. Okay, this is diagonal. So if we guess upper, okay, so all elements below the diagonal must be 0. Okay, so this is the format. Okay, so now we have A. We would like to get A1. Remember, we just applied the single elementary operation, right? And then you can get A2 after some step. You can get AK, and AK like U. Okay, so how can you get this one? Because this is Gaussian elimination, right? You can get U. Okay, so we can say U E, right? U is EK times EK is minus 1, blah, 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 times E2 times E1 times A. Okay, so if I times inverse of K, I write here EK minus 1, blah, 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 E1A. So if here I times EK minus 1, that means inverse of EK is inverse of EK minus 1, blah, 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 inverse of E1. Here we get U and the same, inverse of EK is minus 1, blah, 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 inverse of is 1. Okay, so here delete, blah, blah, delete. So this one become A. Okay, one become A, and this one is U. So that means this one is L. Okay, so to get L, can calculate the products of inverse of E1, blah, 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 times inverse of EK, like this. Okay, like this. L inverse of E1 times inverse of E2 times blah, blah, times inverse of EK. So like this. Okay, but normally when you get U, you can guess L very quickly. We don't need to take this product. Okay, so some students, they are really smart. Okay, and if we have A is L times U, okay, we already know A, right? We already know U, right? So this one lies a linear equation, right? Linear equation. Okay, and then you can get L immediately. For example, if we have A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, we already know A, right? And after finish these steps, you can get U. So U is what? U11, okay, U22, U33. Okay, because this is upper triangular matrix. So this is 0, this is 0, and this is random. We know, right? So now we know U, right? We already get U. U is U11, U12, U13, U22, U23, U33, and this is 0, 0, 0. Okay, and L, we don't know L, we know A, we know U, but we don't know L, but we know the format of L, right? L is L11, L22, L33. Okay, so this is 0, 0, 0. This is L21, L31, L32. Okay, so when we take A is L times U, that means we have three linear equation with some variable. Okay, so we can get the result. For example, if we take L times U, okay, so we can get or I can write here, now we know A is A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, E, L11, L22, L33, L21, L31, L32. Maybe I write here a little bit lower, I22. This is 0, 0, 0. Okay, we don't know this one, right? But we know this one. And then we know U. U is what? U11, U22, U33. Okay, U12, U13, U23. Okay, this is 0, 0, 0. Okay, so you can get L11. Why? Because we know from if we, is that correct? Yes, that's correct. Okay, so for if we take this one times this one, you can get A11, right? A11 E L11 times U11. Okay, all right, right? So we know A11, we know U11, so we can get L11. Okay, and similarly, we can get L21 and L22. L21 is what? Okay, L21 is what? So we have A21, or maybe this one, A12E, the first row and the second column, right? You can get L11 times U12, right? This one times this one. So we also get L11. Or here you can get L11. Okay. And then we have A21. Yeah, A21. E, the second row and the first column, you get L21. Yeah. And times U11. Okay, this one is 0. Okay, so we know A21, we know U11, you can get L21. Okay, similarly, A22. A22 is the second row and the second column, you get L21, U12 plus U22. L22, we already know A22, U12, U22, and L21 from here, you can get L22. And blah blah blah. So it's up to you. You can calculate inverse of one and blah blah blah, and then you can get L, or you just follow the linear equation. You also get L. It's up to you. Okay. Of course, we have many methods to get U. To get L. But yeah, you can use ChatGPT or go somewhere in the website. You can study different methods to factorize A is L times U, but to limit the content of the lectures, I just introduced to you two methods. This is the first one. Okay, and this is the second one. Okay, so we can apply these methods. Okay, for your final exam. Any questions so far? Maybe we have some example to let you use your more understand. Any questions? Okay, so now if no questions, okay, and then so maybe you continue to ask me why we calculate A is L times U. Okay, A is L times U because you can solve the linear systems. Okay, maybe faster. Okay, so we have AX equal B. Okay, and A now become L times U times X equal B, right? Because AC L times U. Okay, so if right, L times U. Okay, so if the first step, if I let Y equal to L U X, okay, I just define Y EU times X. Okay, so after that, I can get L times Y E B. Okay, do we know L? Yes. Yeah. Because we apply factorization method, you can get U and I. So if we know L, B we already know, so you can get Y. Okay, so step 2, you can get Y from this one. Okay, you can get Y. After you know Y, do we know U? Yes. Okay, then we can get X. Okay, so this is the ideas. We get the solution of Ax equal B when we apply the LU factorization. Okay. Yeah. Okay. Any questions so far? Guys, are there any questions from the class? Okay, so if we have no questions, we do some examples. Okay, no questions. Continue. Okay, so now find an LU factorizations of the matrix A. Okay, now we have A. Okay, A is L times U. So first of all, we need to modify A to become U. How can we do that? We apply Gaussian, right? Elimination. Okay, so this is A, and this is A1. Okay, A become A1. A become A1, we do what? We would like to modify here, become 0, right? So that means we apply minus 2 times R1 plus R3 related to R3. So if we apply this step, okay, you can get A1. You can get A1. Right, this is minus 2. So this one is 6. So minus 2 and 2, you get 0. 6 plus minus 10, you get minus 4 and 2. Okay, so now I would like to get A2. How can we do? A2. I wanted to modify this one become 0. So this one is U, right? So A2 is U because all elements below the diagonal is I0, right? I0. So this is upper triangular matrix. So we apply what? Okay, so to let this one become 0, that means we do what? We times 4 with R2 plus R3 related to R3. Okay, so here this is 4, this is 12. So 4 plus minus 4, you get 0, and 12 plus 2, you get 14. So now we already get U. So U is 1 minus 3, 0, 0, 1, 3. Right, and then we have 0, 0, 14. This is U. Okay, so I would like to get L. Okay, and you should remember that U is what? U is E. So if here we have I, how many? A, we have 3 rows and 2 columns. So we have I, 3 rows and 3 columns. Okay, so if we apply the same step here, to I, you get E1, and we apply the same step here, you can get E2, right? So Here I is what? I is 1 0 0 0 0, sorry, 0 1 0 and 0 0 1. So if we apply this step, you can get A1, you know. This is R1, R2, R3. Okay, so minus 2 R1. This is minus 2 0 0 plus R3. So you get 1 0 0. This is 0 1 0 and R minus 2 R1 plus R3 is minus 2 0 1. Okay, so this is 1. Okay. Then we apply the same this one to I, you can get A2. So you get minus, you get what? You get 4R2 plus R3 related to R3. Okay, so this is 4. Okay, and then you get 1 0 0. Okay, 0 1 0. Okay, and then relate to R3. So 4R2 plus R3. 4 plus 0, you get 4. And 0 plus 1, you get 1. So this one is E2. Okay, yeah. So we already have U, right? So U is E2, E1 times A. Okay, so that means L is inverse of E1 times inverse of E2. Okay, so remember that here. And we have the table, right? If we know E, you can get inverse of E very quickly. So if here we times minus 2, you can get E1. So if we would like to get inverse of E1, inverse of A1, you need to take R3, right? Plus 2 R1 related to R3, because this is the table here. Here, okay? If we times C with row I to row and then add row J, so here you should times minus C to row I. Okay, so here we already times minus 2 here, so minus of minus 2 you get 2. Okay, so here that means here you get minus 2. Now you get here is E1 is here, it is 2. Okay, isn't it 2? Yeah, sorry, because yeah, okay, that's okay. So here you then to get E2, inverse of E2. Look, we times 4. So if you get inverse of E2, you get to time minus 4. So you get R3 minus 4R2 related to R3. Okay. Yeah. So minus 4 here. Okay. So here you get 4. So here you just get minus 4. Okay. Or you can apply, right? Yeah, you have this I, and now we have 4 minus 4 R2 plus R3 related to R3. You get minus 4 is 0. So you get 1 0 0 0 1 0, and this one plus this one, right? Minus 4 R2 plus R3. You relate to R3. So minus 4 0, you get minus 4 right here. Okay, so here is inverse of E1 and here is inverse of E2. And then we check the products of inverse of E1 and inverse of E2. You can get here. So here is L. Okay, here is L. Yeah, that's all. Okay, or you can apply the linear equation. Okay, A E L times U. We know A. We know U. So you can get L. Okay, so we have 2 ways. So finally, you can get the factorization of A, okay, to be L times U. Any questions so far? Okay, so let me check. Are there any questions? questions? Try to ask me if you don't understand, and don't be shy. Okay. So yes. Okay. This is U, and then this is L. Okay. Yeah. So now we try to apply A equal to L times U to solve AX equal B. Okay. So here. So I'll take example. Copy it, and I pause here. Okay. Okay, here. So we would like to solve the linear system like this. Okay. Yeah. So how can we do? Okay. We need to modify this one. Okay, becomes AX equal B, right? So A is what? And X is what? And B is what? Okay, now look, for we how many variables? 1, 2, 3. We have x1, x2, x3. So from xb you get -5, -1, and then -20. -5, -1, -20. So here you get 1, -3, right? And here 0. This one is 0, 1, 3. This one is 2, -10, and 2. Am I correct? If I have some mistake, okay, please remind me. Okay, so now this is A. This is matrix X, and this is matrix B. Okay, I would like to modify A become A. Of course, we can apply Gaussian elimination, you get the result directly. Okay, but now we try to use factorization of A. Okay, that's A is L times U. Okay, so now we know A. Okay, A1 -3, 0, 0, 1, 3, 2, -10, 2. Okay, I would like to get A1. Okay, this is R1, R2, R3. So I try to modify A to become U. Okay, so I need to delete 2. How can I do? I time -2 with R1 plus R3 relate to R3. You can get A1. Okay, so if here is -2, right? Here is 6, here is 0, right? -2 times R1, 2, 6, 0. And then this one, but this one, so you get here 1 -3, 0. Just keep it 0, 1, 3. So this one, but this one, you get 0, 6, -10. You get -4, and 0 plus 2, you get 2. Is that correct? I hope so. Okay, so then I would like to modify I1 to become A2. How can we do? Look, I wanted to modify this one to become 0, and this is R1 and 2 R3. So if I time 4 with R2 plus R3 related to R3, okay, yeah, R3. Okay, I can delete this one. Okay, so here you can get A2 is 1 -3, 0, 0, 1, 3. Okay, so if I time here is -4, time 4, right? 4R2, 4, it is 12. Okay, so you can get here is 0, here, 0, here, 14. Okay, so this one is U. This one is U. Now, A, we can get I. I will have 1, 0, 0, 3 rows and 2 columns, so you get I3. Okay, 0, 0, 1. Okay, and now I apply the same step. Okay, I can get E1. Here, the same step. E1 is what? Okay, -2 R1 plus R3 related to R3, so you keep R1, so 1, 0, 0. Okay, we keep I0, 1, 0, right? We just modify I3. So minus 2 here, you get here is minus 2, 0, 1. Okay, minus 2, right? Minus 2. Okay, so, and then I would like to get E2. E1, we apply the same step here to I3. So we just modify R3, so we keep here 1, 0, 0, 0, 1, 0. Okay, we keep R1 and R2, we just modify R3. So you get 4 here, right? 4 is 0. So you get here 0, 4 plus 0 is 4, and 0 is 0 is 1. Okay, yeah. Yeah, so now you get E1 and E2. Okay, so now I would like to calculate inverse of E1 and inverse of E2. So inverse of E1 is what? Okay, so here to get E1, we apply minus 2 R1 plus R3 relate to R3. So when we get inverse of E1, we just modify this one become what? Minus on minus. You get 2 R1 plus R3 relate to R3. Okay, so you can get E inverse of E1, E1, 0, 0, 0, 1, 0, and you get 2, 0, 1. Okay, and similarly, you can get E inverse of E2. Inverse of E2 is here. Okay, look, this is you times 4. So here you need to times inverse of 4R2 plus R3 relate to R3. Okay, so you can get inverse of E2 is 1, 0, 0, 0, 1, 0, 0, minus 4, right? 1. Okay, so now you can get L E what? L E inverse of E1 times inverse of E2. Okay, so we can get what? 1, 0, 0, 0, 1, 0, 2, 0, 1, and E2 is 1, 0, 0, 0, 1, 0, 0, minus 4, 1. Okay, yeah, so you can get what? The result. This one times this one, you can get 1. This one times this one, right? You get 0. Because this is lower, so you just get 0 here. And you know, this one times this one, you get 1. This one times this one, right? This here, this one time, or here, this one time, this one, you get here is 0, 0. This one time, this one, you get 2. This one time, this one, you get what? Minus 4. And this one time, this one, you get what? You get 1. Okay, so this is L. Now you can check. L is 1, 0, 0, 0, 1, 0, 2 minus 4, 1. Okay, here, L. Okay, 1, 0, 0, 0, 1, 0, and 2 minus 4, 1. Okay, so now we already get U. We already get L and U, right? L and U. Okay, so now, now I demonstrate to you, we get the factorization of A. Now we come back here. So finally, we get L and U, right? L, this is L, this one is U. You need to remember the sequence, you know, A is L times U. Okay, and then step 1, you let Y is U times X. We discussed before, right? So AX is B, that A is L times U times X is B. You let here is Y, so you get L times Y is B. Okay, do we know L? Yes. Do we know B? Yes, you can get Y. Okay, so this is L, this is Y, this is B. So, you know, we can get Y. Okay, so Y is Y1, Y2, Y3. So Y1 is minus 5, Y2 is minus 1, and Y3 is minus 14. So this one equal to Y1 is minus 5, Y2 is minus 1, and Y3 is minus 14. Okay, then step 2. So now we get Y. When we know U, you can get X. Okay, now, yeah, this is U. This one is Y. You can get X. So finally, you can X1, X2, X3 equal to minus 5, minus 1, right? Oh, sorry, X1 is 1, 2, and minus 1. This one is 1, X2 is 2. and x3 is minus 1. Okay, this is the result. That's all. Yes. Any questions? Okay, so if we have the linear system with more variable, okay, so LU factorization is the good method, okay, for you to figure out the solution of linear system. Okay. Of course, you can answer directly this question, right? We just apply Gaussian elimination. We also get X. Okay. But why we use LU factorization? Because sometimes the linear system has many variables. Okay. So if we have A, we have A11, A22, blah blah, ANN, we have many variables, so very difficult if we apply Gaussian elimination and you get the result. No, very difficult. Okay, so we just modify A is L times U, and maybe you can solve the computation time to get the solution, okay, of linear systems. Okay, any questions so far? Teacher, is the E2 transformation a continuation of I or a continuation of E1? Okay, yes, I emphasize to use many times. Okay, when we calculate here, when we calculate E1 or E2, okay, we need to apply the elementary row operation to I3. Okay, that means we get E1 from I3. You get E2 from I3. I draw, okay. I draw the arrow here. We cannot get E2 from E1. No. You get E1 and E2 from I3. Please remember it. Okay, yeah, I try to draw the arrow here to remind you, some students make a mistake because they calculate E2 from E1. Okay, this is very stupid. Okay, I emphasize to you many times. Okay, please remember, we calculate E1, E2, blah, blah, blah. EK come from I3. Okay, yeah, we just apply the same elementary operation, but we apply for I to get A. Okay, is it clear for you? It's a good questions. So, for any questions so far? If you have any questions, please ask me, or you ask TA, and TA will repeat to me. Okay. Other questions? Okay, good. Oh, we have exercise. We have exercise to practice. Okay, determine whether the given matrix is elementary or not. Okay, for example, this one. Of course, the matrix, the first condition, the matrix must be a square matrix. This is the constraint, the first constraint, the square matrix. Yes, okay, the square matrix. So all of them are square matrices, right? Now, for example, this one, this is 2 row and 2 columns, so we consider I is 1 0 0 1. So check. This is 1 0, okay, the same, right? This is It's 1 0 1 0 the same. Okay, so if you would like to get -5 and 1, that means with this is R1, this R2, so we just apply one elementary operation because we can time -5 with R1 plus R2 replace to R2. You can get this one, right? -5 plus 0, you get -5. Okay, yeah. So this is elementary matrix. And this one, this is the same. So we just modify this one. How can you get this one? Okay, so if I times -5 with R2 plus R1 related to R1, this is -5. Is that correct? Let me check. Oh, okay, this one is not elementary matrix because the first step, they move they interchange R1 and R2. Okay, they can get 1 0 here. This is 0 1. This is the first step. The second step, they times -5 with R2 plus R1. Okay, -5 with R2 is -5 0. -5 plus 0 is -5 0 1. Okay, so this is not elementary matrix. Okay. Yeah, of course. Just double check. Okay, you can know whether the given matrix is elementary or not. Okay, now find a row operation and the corresponding elementary matrix. Okay, that will restore the given elementary matrix to the identity matrix. Okay, they just ask us to calculate back, okay, the matrix here to become I. Okay, I22. This one is I3. Okay, very easy, just okay. Yeah, find a row, a row operation. Okay. So very easy, we need to delete this one to be 0. Okay, this one is 0. So we just apply what? We just time 3 with R2 plus R1 relate to R1. You can get 0. And we apply the same step with identity matrix. You can get A1. Okay, easy. Yeah. Continue. Use the following matrices. The following matrix here, A, B, C, D, F, and find an elementary matrix E that satisfy the status equation here. Okay. We know A, we know B, we would like to determine E. Okay. Okay, so from A to B, what kind of elementary operation we need? Okay, look, this is 2 minus 7 minus 1. This is A1 5. Oh, that means we interchange R1 and R3. Okay, you can get B. So A is what? A should be interchange R1 and R3. So this one is 0 0 1 0 1 0 and this is 1 0 0. Okay, we interchange, right? Because identity matrix is 1 0 0 0 1 0 0 0 1. This is R1, R2, R3. So when we interchange R1 and R3, you get here. So this one is E. Okay, yeah, very easy, and so on. Okay, exercise 3. Okay, blah blah blah. So I think we focus on this one. Find a sequence of elementary matrices that can be used to write the matrix in row echelon form. What does this mean, row echelon form? Row echelon form mean U, right? U, right? Row echelon form here, row echelon form. So this one is U if we have a square matrix. Okay, this one. So if 1 is 4 and 4, so if we get row echelon form, you can get this is diagonal, right? Diagonal element and upper. So H1 is 0, H1 is random, right? Random. Okay. So this one is U. Okay. This one similar because it is square matrix. Okay. This one is not square matrix, not square matrix, not square matrix, not square matrix. Of course, you can get. Okay. This one is very difficult because we cannot find the sequence of the sequence of elementary matrix because this one is not square matrix. But of course, we can assume this here is any random values, and then we just apply the same elementary operation to I, but meaningless when we determine I is L times U. Okay, just follow the same sequence. The same elementary operation to I, and then you also get elementary matrices. Okay, but when we consider elementary matrices, okay, the matrix here must be a square matrix. Okay. Okay, so for exercise 4, find a sequence of elementary matrix. Okay. Yeah, this one is good because all matrices are square. Okay. Yeah. And then we can get inverse of A, right? We can get the inverse of A. Okay, whose product is given a non-singular matrix. Non-singular doesn't mean invertible matrix. Invertible matrix means we need to determine the inverse of A. Okay, inverse of A. So inverse of A is EK times EK minus 1, blah, 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 times E1 times I. So that means we need to modify this one to become I. Okay, to become I. Okay. So, here, find an LU factorization. Okay, what is a square matrix? Okay, so we can get IC L times U and use an LU factorization of the coefficient matrix to solve the linear system. Okay, so we yeah. Any question for the exercise? Any questions so far? So guys, are there any questions? Okay, so if you have no questions, we continue. Okay, so summary. Okay, yeah, we know A is L times U, and then you can get the solution of AX equal B. Okay, so samples of exam questions like this. Phi and LU factorizations. Okay, yeah. Let me see. Oh, this one we have another. Maybe we skip this one because A is not a square matrix. Okay, so we have another method to get the L and to get L and then the use because A is not a square matrix. Okay, anyway, I will explain to you. So from A we have 4 rows, but here we have 5 columns. Okay, yeah. So I now A is not a square matrix. Okay, so we can apply another methods. Okay, so here L should be 4 and 4, of course, because A is 4, the 5 does mean L times U. Okay, yeah. So here should be 4 and 4, and here should be 4 and 5, right? So here we have 4, so you can get A 4 and 5, okay? So to do that, okay, we have the format, you know, L is 4 and 4, and we know this is a lower matrix, the lower triangular matrix. So the elements above the diagonal must be 0 here. Okay, here. Yeah. And the first column of L is the first column of A divided by the top pivot entries. Okay. So the first columns of A, okay, so the entries is what? And by the top pivot entries, the top pivot entries is what? E2. E2. Okay. So 2 minus 2, you get 1. Minus 4 divided by 2, you get minus 2. 2 minus 2 divided by 2, you get 1. And minus 6 divided by 2, you get minus 3. Okay. So now we keep. Okay. So this is A. This one is A. Okay. So remember this one. Okay. Yeah. So from A, you can get A1, okay, and then A2, and then blah, blah, you get U, okay. We just apply Gaussian elimination, okay. So when we apply Gaussian elimination, you can get U, okay, yeah. Here, you know, we want to modify minus 4 to minus 6, blah, blah, 0, 0, 0, blah, 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 blah. Okay. So after that, you can guess this one. Okay. So this one is like upper triangular matrix if we consider this one, right? Okay, this is the diagonal element. Okay, so all elements below the diagonals must be 0. So this one like like upper triangular matrix if we exclude the glass columns. Okay. Yeah. Then continue. Okay. So here I just copy here. 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 Okay. So now I would like to get L. Okay. L. Here, this is the first column. Okay, you get the first column the same with the first column of A. Here, you know, the first column of A. So if and here you can get the second column of A1. Okay. Yeah, and this one we don't have. Here we don't have the leading entry, so when we consider the next column, so this one you get 2 for the leading entry, so you get 2 4, and this one you can get 5. Okay, so this is the first pivot, the first pivot. Okay, so here you get divided by 2, you get 1 minus 2 1 3, you divide this by 3, you get 1 minus 3 4, blah blah blah. So and then you just copy here, you can get L. Okay, you can get L, and then when we know L and this one is U, so A is AL times U. Okay, so this is the methods of LU factorization if A is not a square matrix. Okay, A is not a square matrix. Any questions so far? Yes, question please. So remember that normally A is a square matrix because we can get the if A is a square matrix, you can get the certain solution. And here, you know, we only have 3 4 equations, 4 rows, but we have 5 columns, so maybe we have many solutions. Okay, and then if we have many solutions, maybe okay, we I mean we don't need to apply factorization of A. Okay, just this one for expansion. Okay, we can follow for this method to factorize matrix A is not a square matrix. Okay. Or as I mentioned before, if you get U, you can get A. Sorry, you can get L based on linear equation. Linear equations. Okay. So if you don't want to follow these steps, that's okay. We just apply Gaussian elimination, you get U. After you get U, we solve linear equation, you can get L. This is the easiest way. Okay, and we don't need to remember some steps here. Okay, so it's up to you. Okay, but for the final exam, I will give you A that is a square matrix because we have more meaning. Okay, and of course we have the certain solution. Otherwise, if we have less equation and more variables, we have many solutions. Okay. So this is the methods, and we need some demonstration. Okay, but now we don't have more times to demonstrate, so you can ask ChatGPT or you read textbooks. Okay, they will explain to you why. Okay, just a method to just easy, to the method, make sure the entries must be one for easy, but of course you can keep this one, that's okay, no problem. Okay, no problem, but we hope we can get the leading entries to be one for easy calculation, okay, for further steps. So just divide this to get one, okay, just mention about it. But of course you can keep this one is 0 0 0 0 0 0, no problem, okay, it is acceptable. Okay, but more more, I mean, the calculation maybe is quite complicated because the little entries is not one, but just modify here, you get one for easy calculation. That's it. Okay, is it clear? There's yes, of course. Yes, of course. Okay, the methods legal for the square matrix. Yes, because for the square matrix, of course, we don't have this one. Okay, because we have for the square matrix, we don't have the column like this because we don't have leading entry. So if we use a square matrix, we cannot see these columns. Okay, we cannot see this column. That's all. Is it clear? Right? Why I say for the square matrix we don't have this one? Very easy. It's because if we consider lower and uppers, we always know, right? We always know the diagonal elements. Okay, the diagonal element, and okay, and because we have leading entries. Okay, and now for a non-square matrix, we need to forget this column because no leading entries. Any questions so far? And okay, so why choose the pivot column after every transformation to reduce? Why we why we choose the top pivot here? Because we can make sure we have the little leading entries always. Okay, and remember that for our LU we have leading entry. Okay, so look at this one. We need to choose the top pivot entries because we can make sure this is leading entries. Okay, this is leading entries. And consider, right, we have 4 row and 4 column leading entries. This is leading entries. So this one is the leading entries. This one is no leading entries. So forget this one. Leading entries. Okay, and here for leading entries. Okay, so to choose the leading entries, or we say the pivot entries, that's very important. If we have A, that is not a square matrix. Okay, like this. Leading entries. So you can get L. Okay, so now this one is here we have LU factorization of A. Now we have five rows and 4 columns. Okay, so if here we have A is E, 5 and 4, L times U, so L must be 5, and U must be 5, 4. Okay, yeah. This one is also non-square matrix. Okay, so now the first column here, the first column, right? 2, 6, 2, 4, minus 6. Okay, little entries. After some steps, it is 0, 0, 0, 0. Look, 0, 0. You can get 3. We copy this one to be here, and then continue. We modify. Okay, this one is no leading entry, 0, blah, 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 0. So now this is leading entry. The leading entries. So you move to here, right? Similar to this one, right? Similar to this one. Here, 2 minus 4, 2, 6, 3 minus 9, 10, 12, okay, 2, 4, 5, something like this. You just copy, okay? So, and then we would like to multiply it with 1, right? 1. So we divide this by 2. You get this 1, this 1, this 1. But remember that for L, finally we have the leading entry. Okay. So now we get 1, 1, 1. Okay. So you should get should be 1 here, and here should be 1 here. Okay, so if I add 1 here, so the other will be 0, 0, 0, 0, 0. Okay, so now we get this one. That means this one for so these columns and this column from identity matrix. Okay, so now you can get L. Okay, and this one you can get U. Okay, so now we have LE 5 rows and 5 columns, and U we have 5 rows and 4 columns. That's all. Okay, so remember that. So for this case, okay, we should make sure the diagonal elements must be non-zero elements. So you should add 2 more columns of the identity matrix. Okay, this is L 5 rows 5 columns, so you get I5, right? 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 0 1 0 and 0 0 0 0 1. Okay, so you just add more columns. Okay, the 4th column and the 5th column into here. Okay, you can get L. That's all. Okay, this is expansion, right? We have A. That's E and N. Or we have A is N times M. Okay, N higher than M or N less than M. Okay, so we can get A is A L times U. So this one is more expansion about factorization of A. Okay. Of course, we have application and some more exercise. Okay, so now we find the LU factorization. Okay, this is a square matrix. Okay, square matrix, 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 square matrix. Okay, otherwise, I mean, for the real applications, okay, we should make sure we have the certain solution. So to get the certain solution, A must be a square matrix. Okay, or if A is not a square matrix, we can apply this step here. Okay, slide, yeah, something like here. Okay, you can get more understanding. Okay, we have applications, but we don't have more time. So when you study electric circuit, Okay, we can apply. Yeah, we can apply the factorization. We can apply the factorization into electrical engineering. Okay, just very basic, you know. We say this one is the system. Okay, so this one is input and output. For input, we need current and voltage. For output, we also need current and voltage. Okay, yeah. So that means here in the matrix A. We don't know, but here is in the matrix A. What's in the matrix A? Okay, if we only consider R1. Okay, and this is in series. So now we get A. We don't know, but we know this is 2 rows and 2 columns because 2 inputs, 2 outputs, we have 2 rows, 2 columns. Okay, so we have I is 1001. Okay, yeah. So for a series circuit, you know this one. How can we know I very easy? Very easy. You know this is V2, I2, and here we know V1, I1. Okay, right. So we know we don't know A. Okay, but look at this one. We know I1 is I2. This series I1 is I2. Okay, and V1 is V2 plus I1 R1 or V2 plus I2 R1. The same. The same because this is the same. Okay, so I1 is I2 if this one is 0. This one is 1. Right? So V2 is V1 minus I1 R1. Okay? So here must be 1 and here is minus R1 here. Okay? So here we have the series circuit. Okay, this is input, this is output. So you can get a 1, 0 minus R1, 1. Okay, we are applying the factorization. So what is this? What is this? What is it? This one is upper. This one is upper, right? So series circuit. Get upper. Okay, now look. Now, okay, this is a shunt. Okay, so you get lower. You get lower matrix, and then here because shunt, so you just time we just take the inversion. Okay, or you get minus 1 over R2. Okay, R2. So now we have L. Now we have U. So I would like to find the relationship between V1, I1, and V3, I3. Okay, now we have the relationship between V1 and I1, and I1, I2, and I3, V3. So if I combine, I would like to find the relationship between V1, I1, and V2, which you get L times U. Okay, you can get I. Okay. So now here I. Okay, so this is the application. We will move if no questions. We take break and we will come back at Now we have 10, 50, and we will come back at 10, no, 11. Okay.